Okay, this will be lecture number 12. We will continue to talk about two spheres. One is breathing, and the other one is traveling sphere. So in the last lecture, we found that for breathing sphere, breathing means that the fluid particles surrounding the sphere will oscillate with the same phase. And if I invite the coordinate x, y, z, whose origin is located at the center of a sphere, okay, normally it has dependency with respect to this angle and that angle, as well as the distance from the center of a sphere. And the wave will propagate through this phase. And since the breathing sphere is symmetric, means that does not have a dependency of theta and phi, the governing equation would simply follow this homogeneous equation. Therefore, we get phi would be proportional to 1 over r, and then unknown amplitude we use a, and then it oscillates with respect to time harmonically, we assumed. Therefore, we can write minus j omega t, and then it is moving away from the center. Therefore, we can say the spatial dependence would be kr. And this a unknown complex amplitude can be obtained by inviting another equation logically, and that another equation should come from boundary condition. Say BC, boundary condition. What kind of boundary condition it is? Okay, when we talk about, for example, limpor, incident wave and reflected wave, and there is a transmitted wave, we apply the two boundary conditions. One is pressure continuity boundary condition, or the pressure difference between two surfaces must follow the Newton's second law. And another boundary condition is fluid particle, the velocity must be continuous on both sides. So in this case, the boundary condition, what we can obviously write is the boundary condition associated with the kinematic boundary condition, not natural boundary condition or forced boundary condition, because what we obviously know that the fluid particle, for example, over here, should be the velocity what it will follow by this assumed solution. So that will determine the assumed amplitude A. So let's write the boundary condition at the surface when r equal A. This is r equal A. So say the velocity in r direction that depends on r and t has to be some magnitude u0 and exponential minus j omega t. I'm sorry, this r has to be A. Okay. So equating this with dphi dr, that is the velocity in r direction, gives us A. Therefore, we got phi, velocity potential, and using the relation between velocity potential and velocity, which is, I said over there, and the pressure with respect to r and t can be obtained by rho 0 d phi dt. So we obtain the pressure. And those velocity and pressure was a function of kr or kr squared. That's what we learned in the last lecture. And it is very useful to see the physics through radiation impedance, ZR. So let's look at the radiation impedance of breathing sphere. Which is simply the pressure at R divided by velocity at any point along the space R. And we found that this is very interesting because it is related with rho 0 c, that is specific impedance of medium. And we remember that if it is rho 0 c, then impedance has only real part, and also it is equal to rho 0 c, means that it radiates sound as if it is plane wave. But because the breathing sphere is not always same as the plane wave, it is modified, and the modification factor that follows to this one is somehow related with 1 plus Ka square and Ka square, that was a real part, and have imaginary part that I remember that was minus j, and numerator is Ka instead of Ka square for the real part, and 1 plus Ka square, same denominator. So this is a scale factor, different with the rho 0 c. Okay, that is quite interesting. And then we look at this scale factor graphically. So seeing this in terms of Kr and the significance of Kr that we have to realize is that Kr is 2 pi over lambda r. This is Kr. Physically means that we are seeing the distance, how far away from the center of a sphere with respect to wavelengths of interest. And the real part behaves like a Ka square over 1 plus Ka square. So if I normalize the radiation impedance with rho 0 C, which is the characteristic impedance of medium, that C means I want to see the radiation impedance compared with the plane wave. That's very interesting observation. That's very interesting way to see the physics associated with the breathing sphere. Okay, now we observe that as k goes high and bigger, this value will approach to 1. This is 1. So in this region, it approached to 1. That means breathing sphere case in a far field, meaning that when we are seeing the wave very far away in terms of wavelengths, it behaves as a plane wave. So this is plane wave region, or we use the important terminology that we call this field is a far field. Far means I am far away from the breathing center of the breathing sphere with respect to wavelengths, and very close to the this point when Kr is very small, which means that the distance is very close to the breathing sphere with respect to wavelengths. The graph has to follow this, and it looks like this behavior. So obviously we can see that the real part in the near field is much smaller than the real part of breathing sphere in the far field. That means when I push, when I breathe, so to generate a wave, the fluid particle that is in phase with pressure is getting smaller and smaller as we approach to the breathing sphere. And this kind of behavior is always happen in most cases. Okay, and let's look at the imaginary part, which is Ka over 1 plus Ka square. And we found that this one and imaginary part shares the common point, that is, if you look at the blue, that is 1, yeah, if I put 1, and that is 1/2, and this graph look like that. So imaginary part increase up to when Kr is 1. What's the meaning of Kr equal 1? Kr equal 1 means 2 pi times r divided lambda is 1. So that means r over lambda is 1 over 2 pi. That means I am away from the center, okay, 1 over 2 pi times wavelength. Okay, so if we that is approximately, we are in the distance which is like a 1/20th of wavelength. In that case, the participation of real part and imaginary part is equally likely. And then it suddenly decreases. The imaginary contribution of imaginary part is getting smaller and smaller. So for the noise control purposes, we would like to use this kind of behavior. For radiation purposes, we would like to use this far field behavior. And this region we call the near field. So what it means, when you hear this sound very near to the speaker, for example, what you will hear is this kind of behavior. But if you far away from the speaker, you will hear this kind of behavior. That's what we learned in the last lecture. Okay, emphasize again. Mathematically, this one has 2 parts, and the scale is KR. Okay, what if I substitute R with A? What does it mean? Then, when R equal A, simply Z R equal A, that would be equal to rho 0 C, and then I have Ka square. Sorry, this should be Kr. Mistake. This is Kr and Kr. Sorry, this is Kr and Kr. I confused. Nobody picked up my mistake this time. Okay, that has to be Ka square divided by 1 plus Ka square minus J Ka divided by 1 plus Ka square. Therefore, it depends on Ka. What's the meaning of Ka? Ka is 2 pi A over lambda. What does it mean by this? Compare with that, R over lambda. That means the size of radiator has to be seen in terms of wavelengths. Okay, that's interesting. Okay, I have a breathing sphere, and I want to generate like a 100 hertz. Then the wavelength should be more than 3 meters, 3.4, usual case. And if size is like this size, then A over lambda would be very small. That means real part is negligible, and imaginary part is dominating. What does it mean? That means when we have a radiator whose size is much, much smaller than radiator, it is not governed by real part. It is governed by imaginary part. That means it's not good radiator. We will see more details about that. And basically graph will follow the graph which we saw over there. But in this case, the wave has to be seen in terms of Ka. And this is radiation impedance when R equal A divided by rho 0 C. The physical meaning of this is exactly same as the driving point impedance that we studied before. So again, the real part approach to 1 as Ka is getting large and large, and the imaginary part will approach to zero as K becomes large and large. And again, this is far field. Far field? far field? Do you think that is correct description? No. No longer field concept. This area, we say efficient radiation. Because we have only real part that approach to 1. This is very important concept. And this area is not efficient. And those regions, I emphasize again, controlled by Ka. Okay. Then, practically, it implies many things. For subwoofer, of course, woofer does not normally look like a breathing sphere. But for low frequency sound generator, normally, for example, some hi-fi audio system, they want to generate like a 20 hertz up to a few hundred, like 10 hertz. The wavelength is so large. So to make an efficient radiator, we have to go this region. That means the radiator has to be very large. Therefore, subwoofer normally is very large, okay, to get a high radiation. For example, for tweeter, 1 kilohertz or 5 kilohertz, the wavelength of 5 kilohertz is what? 6 centimeter or 7 centimeter, very small. Okay, therefore, we don't have to design a radiator, big radiator. Small radiator would be sufficient enough. Okay, that's sort of review of the last lecture. Also, we put some, more physical insight about the impedance. Okay. Let's look at this with respect to some other physical measure.